Morning, afternoon, or evening, depending on where you are. This is my second attempt at day 7 here. I started one earlier, but kind of had some technical issues. So I'm going to give it another try here. Hopefully the internet will stay good. And what we're going to look at today is we're going to get into, we're going to move out of particle physics now. And we're going to be looking at modern physics in terms of not the necessary particles, but the development of the speed of light. Okay, and there's 3 steps in here that we're going to look at. We're going to look at Maxwell's electromagnetic radiation. We're going to look at Michelson's experiment and his interferometer. And we're going to look at special relativity. Hopefully we can get through all 3 of those. Let me just get my preview up here. Show my preview. It's not really showing too good here, but at least it gives me the time. Hopefully it's still working. You may not see me today, I don't know, but that won't matter. Okay, so let's go ahead and set this up. Attempt number 2. Day 7 in modern physics. And we're going to be looking at 3 things. We're going to first look at Maxwell's theory EMR. Then we're going to be looking at Michelson's experiment. Prove this ether theory they used to have way back in the day. And then we're going to be looking at, if we get time, we'll get into special relativity, which has to be developed after the Michelson-Morley experiments happened. And Michelson-Morley did a couple of different experiments, but the one that we're going to be interested in is they're trying to measure this luminous ether, okay, which isn't actually exist. Anyways. Okay, so let's go ahead then and let's take a look at the beginnings of EMR theory first. So basically what EMR theory was, electromagnetic radiation theory. And Maxwell was the first guy to come up with, now there was a guy named Michael Faraday, which happens to be my favorite scientist, who believed that everything in nature is unified, okay, that everything fits together somehow. And there was a lot of these guys that believed, okay, there's got to be a connection or a relationship between light, electricity, and magnetism. So he came up and he said, well, these things are all connected, okay? Now, he was able to come up with a couple of postulates, or one postulate, or prove or show it, one postulate or 2 on that basically went into the development of this electromagnetic radiation theory. And then it was developed even further by Maxwell later on, and it basically led to the idea that light was an electromagnetic radiation. So the first thing that happens here is that, I guess I should do Michelson's experiment first, but first thing that happens here is you have to know the history of what was going on back in the day. So back in the day, pre-1850s, 1860s, they thought that there was a substance in space called the ether. or AR, and this was a substance that allowed light to propagate through it in a wave motion and particle motion. They knew that it had wave properties and it also had particle properties because of Young's experiment and so forth and things like that. So they thought, well, there's got to be this ether, and they also used that ether to describe how heat was created and transferred and things like that, which got disproved as well later on, because they didn't know about atoms, they didn't know about nuclear particles, they didn't know about neutrons and all that kind of stuff. Okay, so that wasn't discovered yet. So they had this ether idea. So what they did then was Michelson was the first person to come out, and he produced an electromagnetic theory, which then basically gave the idea that light was an electromagnetic wave. Okay, and that was a big idea. Okay, so let's go through what kind of Maxwell's the EMR theory has in it. So there's four ideas here. First idea was proposed by Faraday. Okay, and he said that when you have an electric, let's get this one right. When you have a magnetic field, can produce an electric current. Okay. And another guy called Stead, all right, he said the opposite of that. An electric current will produce a magnetic field. We know that because we did magnetic fields already. I think actually that came first. Okay, and then along comes Maxwell. Developed this theory really further, the EMR theory. He came up with two ideas. He said that a changing electric field changing electric field in space, the magnitude of that field is proportional to the rate of the electric field change. The magnitude of the magnetic field the size, so that we don't have to worry. The size of the magnetic field is proportional to the rate of change of the electric field. Okay, mathematically, okay, it looks like this. The magnetic field is proportional to the change in an electric field over time. For a changing magnetic field, he's got the same idea. So the second one is a change for a changing magnetic field size of the electric field proportional to the rate of change of the magnetic field. So that looks like this. Okay. So if we have a changing electric field, the magnitude of this electric field, E, is going to be proportional to the changing magnetic field. Oops, sorry, I forgot the change symbol. Over time. Okay, so that's what he came up with. And to explain the last two principles, he had that in there, he had to come up with something that would work. So this led him to believe, or proved, or helped prove, I guess, not proved, that light was an electromagnetic radiation. Just hang on for a second. I'm going to pause here, answer a quick question on email, and I'll be right back. Okay, so these last two principles, as I was saying, basically set up, as Maxwell put it, because a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. He said that these two last principles would set up an unending chain of events, okay? And he called it an electromagnetic wave. So Maxwell stated, Maxwell's last two principles state set up, let's say, not state, sequence of events. Okay, and the electromagnetic radiation and the electric field and the magnetic field will always be at right angles to each other, as we know as well. So this unending sequence of events, he called these called it an electromagnetic wave. So what does it look like? Like this. Okay, if we just draw. Okay, so if we have, I should use maybe an arrow. No, this will be working. So if we go like this and kind of get this at right angle to it, like that. Okay, and if we say, oh, we need one more line to make this good. Okay, so if we say that the one wave is generated like this, okay, and then we put the other one is generated like this. Okay, this one's up and down, and this is a magnetic field. Okay, I should probably put this one, I should redraw this one a little bit better here. It's got to be more up and down, not off to the side like that. Let's draw that a little better. So this one here is this way, along this plane here. And then we got to do one that's along this plane. So let's kind of go, oh, let's do it in red. Let's go more like this. That's up and down. So this one's going up and down. This one's going side to side. So that's an electromagnetic radiation. This one's generating this one, and that one's generating that one. So it's an unending series of propagations, and that's an electromagnetic wave. Let's call it an EM wave. Okay, and then he actually went as far to calculate the speed of this propagation, and lo and behold, it was speed of light. Okay, so in the end, he was able to say that these electromagnetic radiation waves light is part of the EMR spectrum. So this led to the belief. This led to light being in the EMR spectrum. Okay, so that was the first major discovery that helped out. So what is the EMR spectrum? So if you're looking at it, we've got radio waves, which are long, and then radio waves, and then you have microwaves. Then we have infrared, I believe. Yep, infrared. Okay, then we have our visible light. Okay, and on the other side of visible light, we have the ultraviolet. And then after that is X-rays and gamma rays. Okay, and this was short wavelengths. And this is all part of this electromagnetic wave generation. Okay, and so that led to light being in there. Okay, now the next thing that happened then, okay, and this is the interesting part here. Okay, they discovered, okay, well, this in combination with the next experiment kind of helped push the idea of special relativity. In fact, the next experiment we talk about is often considered the most famous failed experiment in history. The Michelson-Morley experiment. And what they were doing was they were trying to measure the speed of light relative to the ether they believed existed. Okay, so what they did was they split a beam of light, shot it into, they called it Michelson's interferometer, but shot it up in a certain way and had it bounce back. And they had light traveling this way, and then light traveling this way. And what should have happened if there's a moving ether, as they believed, or a medium that this light is traveling through, that these should have a phase shift, because it should take longer to go crosswind than upwind and downwind. Or we got it backwards, I guess. one will take longer than the other, and then there should be, and what they found out was it didn't. Okay, so let's move on to Michelson's Morley experiment. So the next thing that we're going to talk about is the Michelson-Morley experiment. Now there's a couple of them. There's the one with the rotating mirror that you probably talked about in grade 11. And then there's one with the beam splitting, which we're going to talk about now. Maybe we'll do both here. So what happens here is they were attempting to measure speed of light relative, and you'll hear this relative a lot when we talk about relativity, to the ether. I think it's AR or ER at the end. I can't remember how they spelled ether. And this ether was, no, I think it's ER. And they believe that this ether existed in space and it was a medium that light was able to travel through. Okay, and they also used it to describe heat as well. Okay, now what happens is they designed this experiment and it just fails. They can't measure anything. In fact, it was so bad they did it. They improved it, got more money, improved the equipment, did it again, same thing. Okay, so what the experiment was they were, let me get my drawing up here. Okay, so they made an interferometer. So let me just do the basic background first, and then we'll draw it out. Okay, so they created the interferometer. Which measured the speed of light in perpendicular directions. They theorized, they believed that there should be a phase shift or a shift. We'll say that there would be a difference in speeds of the light due to the ether, okay, traveling in moving ether. So that they thought light going this way and light going this way should be different because Earth is rotating, and if ether in space is going like this, and Earth is going like this. As you're going this way, you're going across the ether, and this way you're going with the ether. So there should be a measurable difference in the speed of light, if you believe in this ether theory, right? And everybody did at the time. Okay, So what they did was it set up his interferometer. We'll just do a real basic drawing because that's my skill set. So they had an observer. It's skinny so I can draw it, please. And an observer down here. Okay, and they shot this light. It was not a laser. It was a source of yellow light, sodium light or something like that. I can't remember. And this is and then he had a splitter. A splitter mirror. Okay, and then he had one mirror over here. And this is all encased inside a frame. And a mirror here. So this light came in here. Let's use different. Let's use arrows here. So light came here, hit this splitter, then it went there and back to the observer, and then part of it went here. And these were equal distances, and back to the observer. And this light should have been, these two lights, the perpendicular light should be out of phase. Okay, so there should be some fringes there if you remember great physical science 20 stuff. Okay, so this is the path of light. Okay, and what they found was that what they thought was going to happen is that they expected the two light beams to be out of phase. Okay, one would take longer than the other. Even though the distance were the same, one takes longer due to the ether. Oops, I spelled the ether wrong. It's A. There we go. Okay. And what happened was that didn't happen. Okay. So they had a null result. Let's see what it's. The result is called the null result and was a great puzzle. Okay. So I'll just read a little bit of from my source here. It says, Michelson and Morley designed an experiment to measure the speed of light relative to the ether. What they did was compare the speeds of lights traveling in two particular directions relative to the Earth's motion. The measurement of the speed of light depending upon how their apparatus was orientated with respect to the ether wind. Okay, so they believe that there's this ether wind flowing through here. Okay, and to detect such a small difference in speed, Michelson and Morley used an interferometer that produced an interference pattern between the two parts of the split beam of the light moving in different directions with respect to the ether wave. Any small differences in the velocity of light along the two paths would be indicated by a change in great importance of the experiment was that it was a failure to show that what was expected. There was no change in the interference pattern. The speed of light was the same whether it traveled parallel or perpendicular to the ether wind. Okay, and this is where the theory of special relativity steps in, saying that the speed of light is constant, and also that there is no ether that exists in outer space. Okay, reading along here a little bit more, it says the idea is like a boat on a river. The boat is moving with the water. It will travel a different speed than it will when it's moving perpendicular to the water's movement. Okay, so and that didn't happen. Okay, so they found that there was no interference pattern down here, and basically the basic idea that they found out, their big idea, okay, was that there was no apparent difference in speed of light moving in perpendicular directions to the Earth. Okay, thus, it was puzzling to them, not verifying the ether wind theory. So it was considered the greatest failed experiment. So then this is where special relativity steps in. So then Einstein comes around in 1905 and he develops his special relativity theory. So special relativity comes in. So in 1905, Einstein develops a special relativity. Okay, and that's in response to looking at the speed of light and thinking about it. So what Einstein basically said, he says, well, what if I was on a ray of light? And, what would I see? That's kind of how he thought of it. And he came up with special relativity. Now, special relativity has two main, let's do this on the next page here. Let's take this and copy this up into the next page here. All right, so what he says is that he comes up with the first big postulate. He says that in special relativity, there's two big postulates. The first one is that the speed of light in space is the same for every observer, regardless of which frame of reference they're in. Okay, and if you're thinking of frame of reference, you think of it like this. Okay, if I'm on a train and I'm playing pool or something, that train is moving and I hit the ball. Okay, I hit it with a certain amount of force and whatever, and all those forces are within that frame of reference of the train. So the ball seems to be moving to the right or whatever. Let's say I hit it to the right. Okay, if the train is moving to the left, the person standing outside of the train would see the ball, depending on how hard I hit it, would see the ball moving to the left rather than the right. So his frame of reference is different than mine. So that's what we're talking about when we talk about frames of reference. Okay, so let's give it the two postulates here. The first postulate is that the speed of light in space is constant. Okay, for all observers. Regardless of the motion of the source or the observer. Big one, okay? Because if you say the speed of light is constant, okay, so we know that's a big one because we know this distance over time equals velocity. If you say this is constant, okay, and then there's a change in here, that means that one of these two things has to be changeable, okay? If this is a constant, okay, distance or time has to be able to change, right? Shrink in order to keep this the same. If you're in a different frame of reference, right? If you go into a different frame of reference, and this has to be the same in every frame. So if you go outside of the frame of reference, and this is where you get into the frame of reference that travels close to the speed of light, right? This is constant. It has to be the same in the other frame of reference if you go out of the frame of reference that's not going to the speed of light. So that means time has to be super dilated in order for the speed of light to remain constant. Okay, and that's where that time dilation stuff comes into play. Okay. Okay, and we use c for the speed of light. Okay, so the second postulate that he said was, make sure I get it right here, the laws of physics are all uniformly moving, the laws of physics in all uniformly moving frames of reference are the same. Okay. And all, let's get it right here, and all uniformly if you're going at the same speed and you're in this frame of reference, then the laws of physics will be the same. If you're going at different speeds, laws of physics change a little bit. Okay. So let me read you a little bit about Einstein's special theory from my source here. Okay, it says, in order for the second postulate to be correct without breaking the first postulate, there are some interesting conclusions. If velocity is absolute, then distance and or time cannot be absolute. Okay, and that's what I'm saying earlier. Velocity is equal to distance divided by time. If v does not change and is absolute, then the distance and or time must change. That is, distance and time depends on the frame of reference. Okay, to use time as an example, time is not the same in all frames of reference. Okay, this is illustrated by the story of the twins. One twin was to travel into space. From the twins' calculation, the trip would take 50 years. The twins were already 25. Therefore, when they returned to Earth, they would be 75. Neither twin wanted to make the journey, but one had to. If it should be noted that the spacecraft to be used could travel at a speed just under the speed of light. 50 years passed. 50 years passed. The twin that remained on Earth was an old man, but when his twin stepped off the spacecraft, he still looked 25. Time in the two frames of reference was not the same. 50 years passed on Earth, but only a few months passed on the spacecraft. Time, according to Einstein's special theory of relativity, is not absolute. In the same way, mass depends on the frame of reference, is not absolute. as far as we're concerned in our physics, mass, it is mass that we must deal with. Mass, like time, depends on the speed at which it's traveling. Mass increases with speed according to the following relativity. Okay, so from that reading, that's where that twin paradox comes in, right? So from these two postulates or ideas, special relativity, we know this will be the last thing I can do today because we're already at 40 minutes here. We know that speed of light is constant. In all frames of reference. Therefore, time is not constant in all frames of reference. Okay, the closer to the speed of light you get, that up in case my face is there, the slower time passes. Okay. And we'll talk about the mass one later, but that's as far as I can really go. I'm right into 42 minutes already, and that's the general idea of some modern physics ideas. So just to summarize, okay, Maxwell came up with EMR theory, which related magnetic and electric fields, and then these magnetic and electric fields would propagate each other, and this allowed for universal propagation. Okay, and that's why, and then that led to an EM wave theory, and then thus light is thought of as an electromagnetic wave. It fits into the spectrum. Then along comes Michelson-Morley. They're trying to measure the speed of light with respect to this believed ether that's in outer space so that light can travel through it. And they find that no, there's no difference between the speed of light going this way or that way. And then Einstein takes that a little bit further in his special relativity and says that the speed of light is constant no matter how fast you are going in whatever frame you are in. It's the same. And then therefore that means that if the speed of light is constant, then of course time is not absolute. It can change depending on the frame of reference that you're in. And that's where we're going to stop today.